First of all, this is the work of Pallav Kant, a PhD student co-supervised with Anne Jewell here in Manchester, and Alice Thompson, who is in the audience somewhere, as a colleague who contributed a lot to the model development in this work. And what you see here are successive droplets being deposited in a pixel, and I'll explain why we're interested in that in a second. And these droplets are being deposited by an inkjet printer, and the beauty of inkjet printers is that you can deliver a really precise volume, in our case about 7.6 picolitres, plus or minus, in precisely the way you want it if you've got good enough control on your print head. So you move it around, you put the droplets down, and the industrial co-sponsors of this case studentship, CDT, they're interested in POLED displays. So what they want to do is put down a polymer ink, there's polymer in the ink in some solvent, and get a uniform film of this electroluminescent ink in pixel wells. And of course, put the ink exactly where you want it, job done, except that fluid flows. So after you've deposited it, there's a redistribution on the substrate. And then, of course, in the longer term, there's evaporation as the solvent goes, and the polymer ends up where you want it to be, or it doesn't. And that was their problem. So I'm just going to concentrate here on the redistribution case. And a little bit of careful thought, by Alice mainly, but all of us, tells you that you have to have contact angle hysteresis if you don't just want everything to accumulate in a hemisphere. So if you stick down a droplet, what I mean by contact angles here is it's the angle at which the droplet hits the substrate, and if you increase it beyond the static angle, it'll start moving, and if you decrease, it'll start moving back. And contact angle hysteresis means the angle at which it starts moving when you increase is different from the angle when it starts moving when you decrease. So if you've got contact angle hysteresis, you can get different types of equilibrium configurations. And the idea is then that you want to use variations in the topography and the wettability, the contact angle, to direct and contain the fluid. So here are the pixels. They're a couple hundred microns by 63 microns. Inside is hydrophilic, which means this is a side view. You've got a low contact angle. This is the pixel around here. And outside, it's hydrophobic, so you've got a relatively high contact angle. It's not super hydrophobic. This is a side view SEM. The depth of these pixels is 1.3 microns, which, for those of you who can't do the calculation in your head, is about 10% of the in-flight radius of these droplets. The substrates were manufactured by CDT in their clean room. And the question, I'm going to concentrate on one question in this talk, because it's only 10 minutes, and that is, which matters more? What's more important for controlling these things, the topography change or the wettability change? So here's the experimental setup. It's a combined experimental and theoretical study, and the most important thing to take from this is we can look at it from below and from the side. Pallav set this up, I should say. And here's the model, and it really is an extremely simple model. We've seen in other talks in this conference that droplet impact is a complicated process. And it's hard to model, and it's difficult, and fortunately, for the problems we're interested in, the scales we're at, it doesn't matter so much. So here's the model. Basically, we're going to assume that the droplet is always in equilibrium. So you solve Young-Laplace. When you assume a thin film, the curvature gets replaced by the Laplacian of the height, and then we have a volume constraint that tells us what the pressure is. So this droplet, you know where the contact line is. You solve to find the equilibrium shape. And then the only movement comes in through the kinematic condition, where you advance the contact line according to some spreading law. And what we found is that actually Cox-Voinov, this cubic law, is a pretty good approximation. The blue line that you can barely see is the Cox-Voinov law, and the red lines are results from spreading experiments on the substrate. And it's really very good. So you solve this system, or we solve this system, using a finite element method in our open source library, umflib. And of course, what I haven't told you, that's fine if we've got a fixed droplet of fluid, but what about these new droplets coming in? Well, as I've already said, the impact dynamics is much faster than the spreading timescales. So the way we treat this is to just lump all of this impact into some parameter that modifies the deposited radius. So a droplet comes down, something complicated happens, and then we model that you've got a hemisphere stuck on the surface with some radius fraction phi. When you look at the experimental data, you find that for our systems, this is remarkably constant. It's about 0.8. If you don't like that idea, and you may well not, but my analogy is it's like a coefficient of restitution when you do elastic and inelastic collisions. Fully modeling that problem is really hard, but we all know, or we may remember, that you can approximate it using some approximate percentage. Anyway, We drop these new volumes down. You have to be a little bit careful with smoothing the new volume on, and we choose the smoothing so that it matches as closely as we can the experimental setup when viewed from below. So how well does this model work? Well, here's spreading of a single droplet in a pixel. The red line is the prediction of the model. The false color blue is the experiment. Time goes like that and then like that. And what I hope you'll agree is that actually it's not bad at getting the shape of the droplet right. What it's not so good at is getting the time scale right, and that's because we've neglected all kinds of viscous effects which slow things down. So the model is faster because there's no viscosity in here at all. So now to that question, topography versus wettability. So what I'm showing you here, same thing, the red line is the model, the false color is the experiment viewed from below. We've got a droplet spacing about 25 microns. Contact angle inside is 7 degrees, give or take. This is deposited on a flat substrate outside of where the pixels are, so it's the same sample. That's really important to get the wettability consistent. We've got uniform wettability here, but this is outside the pixel, this is inside the pixel. And essentially what I want you to pick up here is that you get a little bit of enhanced spreading when the droplet interacts with the sidewalls. And that's basically because you will have forgotten, but when the angle was defined, there's an n dot grad b where b is the topography. And that's positive when you go to a rising slope, which means that you get a higher contact angle, which means according to our spreading law, that means you get faster spreading. So that's what's going on. Note that there's some spillage outside the pixel here. And this is very, very sensitive to droplet placement. So if you just have topography, then you will spread, you'll fill the pixel, but it's very, very sensitive and you'll get overspill, which is not what is desired. So if you vary the wettability, if you allow yourself to have different contact angles on the inside and the outside, then that can add robustness, because if we make the outside hydrophobic, and in particular if we raise the receding contact angle, then here's a time sequence showing you that if you get a droplet in the wrong place, the wettability gradient will drive it back inside the pixel. So the question is then, okay, if we just have wettability variations, is that enough to do what we want? Uniformly fill the pixel, have no spillage. Having just wettability variations with no topography is really difficult to manufacture, and certainly couldn't do it with the processes they had at CDT. But we can do it with the model, which I've hopefully convinced you doesn't do a bad job. So same sort of thing, but no experiments here. Time going down like this. There are some questions as to what should we choose for the contact angle and the equivalent of the sidewall, so we just chose some sort of uniform intermediate value, and it's a tangent profile. So there's no spillage, but what I'd like you to notice is you don't get this enhanced spreading effect, so the pixel is underfilled. Now if we put them both together, so now we can do both experiments and the model again, and what you see, I'm going this way, the fluid is contained, that's the wettability variations, and we completely fill the pixel, so we have topography-aided spreading. And to reinforce that point I made about the effective contact angle changing, this graph shows the contact angle measured along the sidewall as the droplet spread. So this is, the lines are for successive droplets going in. The green, that's tricky to see, is if there's only a variation in wettability, and if you add the topography, you get an additional about 50-degree bump in the angle, which is what enhances the spreading. So the conclusions are that we've got this new experimental setup for visualizing inkjet printing, this simple spreading model, and I should say, I mean, we're not the only ones who've done spreading models. There are lots of them out there, but this one allows drop-by-drop comparison with the experiments. So it predicts the fluid morphology, but it underestimates the time scale. But if you're only interested in where it ends up, it seems to do a reasonable job. And this could be a useful predictive tool for printed electronic device design, because it's quick and easy to run. For our pixel geometry, we find that wettability variations give you the confinement, topography variations enhance the spreading, but you need both of them to robustly and uniformly-ish fill the pixel. And as it happens, as I already said, it's actually really difficult to avoid having both, and the way that the manufacturer works in this case is they complement each other. The paper has literally just been accepted, as in on Monday. It is available online, it's got a DOI, and I'm happy. All the details are in there, and I'm happy to take any questions. Thank you.
Okay, lots of times, lots of questions. Yeah, go ahead.
So in your application,
Yeah.
when you're filling up OLED pixels or polymer pixels, is it necessary that the base of the pixel be flat?
No, but you could curve, but then that becomes much more difficult to manufacture in a robust way with the way that they start with a flat slide and then you functionalize it and then you add in it's soft lithography is essentially what they do. You put down the mask and then you go. But you could do something more complicated, I'm sure.
Glenn first and Steve.
So I guess the shape of the topography is to use corner delete in order to...
Absolutely, yeah.
Why wouldn't you just make the edges slightly manufacturing? That should contain that. It's already there.
They did that. They ended up with a really complicated bank shape. And the trouble was, it's the robustness question. When you go on the outside, sort of getting it round and then in, they found they had more issues with it missing and going wrong. Now, I don't know the ins and outs of it. The other thing to say is that this, although corner spreading helps you, this isn't only corner spreading. It's the additional edge effect because of the change in contact angle. You get an enhanced case when you've got concussion fin, but that's for really low contact angles.
Okay, quick question from Stephen.
What matters is after you've dried it.
Yes, what matters is after you've dried it, and that's a whole different ballgame, but you've got to know the initial conditions for the evaporation problem.
Okay, let's take Andrew.
Thank you.
Hi, my name is Liam. I'm a PhD student from Queensland University of Technology in Brisbane, Australia. And today I'm going to be discussing a numerical scheme for controlling instabilities in, let's say, non-standard Healy-Shaw flows. So Healy-Shaw cells is a pretty classic problem in interfacial dynamics. So essentially, experimentally, what we consider is two flat plates separated by a small gap. And I'm going to fill this small gap up with a viscous fluid. Then I'm going to inject into this viscous fluid a inviscid bubble. And that's going to create an interface between the two fluids. And as I inject the bubble, that interface expands. The reason that people care about this problem largely is due to this picture here, is what happens when I inject my bubble. The interface between my two fluids is unstable, and I get what's called viscous fingering, which is kind of these patterns here characterized by their tree branching-like structure and kip splitting. So this problem has existed for decades, and in kind of recent times, people have been asking, well, what happens if I want to control my instabilities? And most of the strategies that have been developed, employ a time-dependent injection rate of my bubble. However, in the last, say, 5 to 10 years or so, people have kind of been getting a bit more creative with their methodology, and they've been using geometry manipulation. So essentially, what they do is they take some aspects of the plates and modify it. So today I'm going to be considering two manipulations. The first is what happens is when I'm injecting my bubble, what happens if I'm lifting my plate at the same time. And the second manipulation I'll consider is the tapered plates. So my plates are stationary, but the top plate probably looks like a traffic cone now instead of being parallel. So the standard model for Healy-Shaw flow is very well established at this point, and what I'm considering here is basically a more generalized version. So in this case, if I consider the blue region to be the viscous fluid, then my equation for pressure here is now an elliptic PDE, which P is pressure, B is the height of the plates. So if B is a constant, which traditionally it is, that just reduces to Laplace's equation. In terms of boundary conditions on the bubble, I have two. The bottom one here is essentially just modeling surface tension, so it's kind of referred to as the dynamic boundary condition. And the second one here is called the kinematic boundary condition, which is essentially the thing that makes the interface move. Finally, I'm going to consider the far-field boundary condition, which essentially is just prescribing the velocity of my fluid at infinity, which just means that my bubble is increasing, its volume is increasing at a prescribed rate of q. So as I said, people have kind of considered these two geometry manipulations in the last 5 years, primarily through linear stability analysis and experiments, but so far there hasn't really been much in the way of fully nonlinear simulations. So today I'm going to try and propose a flexible numerical scheme which is able to solve this problem and investigate the effectiveness of these strategies. So the methodology for solving the classic Healy-Shor problem is pretty well established. Since we usually have Laplace's equation in the viscous fluid region, we usually resort to, say, a boundary integral method. But since for our generalized model, we don't have Laplace's equation, we have kind of a general elliptic PDE. So boundary integral methods become less suitable. So what I'm going to incorporate instead is what's called the level set method. So it's what's called a front capturing scheme, as opposed to, say, a front tracking scheme, which is kind of what the boundary integral method is. And how it works essentially is if I consider, so let's say, 3 interfaces here, I'm not going to parameterize them explicitly. Instead, I want to introduce a higher dimensional, say, surface, which I'll call phi, which essentially the 0 level set of this function represents my 3 interfaces. So in some sense, I've added an extra dimension to my problem, which kind of sounds like a lot more work, and it is. But the payoff to that is by representing my curve with a hypersurface, I'm able to represent much more complicated interfaces, which is exactly what I want for this kind of problem. And I don't have to worry about reparameterizing my interface. I don't have to worry about mesh generation. And by doing so, I'm able to solve my problem on a uniform mesh, essentially. OK, so first of all, let's just kind of do a bit of recap of the time-dependent injection rate strategies. So this is kind of the parallel plates, not lifting in time or anything. So as I said, most people use linear stability analysis to study Healy-Shor flow. And how it works is essentially if S is my interface, what I'm going to do is I'm going to take the circular solution to this problem, and I'm just going to add in a small sinusoidal perturbation, where essentially the most important term here is this gamma n, and that's just the amplitude of my perturbation. And what I want to ask is, how can I choose my injection rate Q such that I control the development of my instabilities? So one of the strategies which comes out from doing this, if you follow the working through, is if linear stability analysis predicts that if I inject my fluid, my bubble, at a rate of t to the negative a third, I should actually see a constant number of fingers form, so I'm preventing tip splitting from occurring. So using a numerical scheme, let's test that. So on the left here, this is just the classic constant injection rate problem. And we can see that the level set method does a pretty good job at incorporating all, the tip splitting behavior that we saw in the first slide, which is good. And then in the second picture here, what we do is we try out the power law injection rate. And in fact, what we notice is we get a constant number of fingers forming, which is consistent with linear stability analysis. So this isn't a new result. People have kind of tested this experimentally and numerically. But it is good just to make sure that our scheme is capable of reproducing this. OK, so what about the lifting plate problem? So a few years ago, a paper by Zhong Zhang and collaborators, they essentially did linear stability analysis, but then asked the question, what happens if my plates move in time and I'm injecting at a constant injection rate? And what they found was that if you lift your plates according to the power law t to the 1 on 7, you should be able to control the number of fingers that you get, just like we saw on the previous slide. So they tested this experimentally. So the first figure here is just the classic stationary plates. And then for the next 3, what they did is they lift the plates at the same rate, but they changed the injection rate. And what they found was, indeed, you see a constant number of fingers. So here's 8, 6 if I inject a little slower, and 1 if I inject slower again. So what we do is we take the experimental parameters in the paper and we chuck it into our numerical scheme, and essentially what we see is 8, 6, and 1 fingers. That's good. So our scheme is able to quantitatively describe the experimental results, which is exactly what we wanted to see. So for the final geometry manipulation, this is the tapered plates problem. So this is where we kind of have a traffic cone like top plate. So in experiments done actually very recently this year, the authors of this paper, they said, well, what happens if I want to reduce the fingerings that I see by introducing this tapering? And so what they did was they considered the classic parallel plate problem, and then they considered the same problem but now with tapered plates. And note that they chose the taper for the left and right-hand cases such that the same amount of bubble is being injected at the same amount of time at the same rate. So this is actually, you couldn't tell from this angle, but this is actually the same volume. And what they found was by choosing their tapering carefully, they were actually not only able to partially suppress, but they're actually able to completely suppress fingering without having to inject at a slower rate. So once again, we take their experimental parameters, we chuck it into our code, and just as we hoped, we see essentially the same thing. So once again, our code is able to do a really good job at reproducing experimental findings. Okay. So just to conclude quickly, so essentially what I've done is I've considered a generalized Healy-Shaw model, which has been studied previously, but now we have fully nonlinear simulations which are able to replicate both linear stability analysis and experiments. Moving forward, there's obviously lots more manipulations to consider. One of them is the elastic membrane problem, but there's actually several talks in this session about that, so I won't step on anyone's toes. Another one I've been considering is what happens if we have a finite amount of viscous fluid, such that we have an inner and an outer boundary, so we have two interfaces that we need to solve for. And so I've been playing around with extending my level set code to allow for multiple interfaces. And essentially what I've found is preliminary results are matching quite well with experimental results. Thank you.
Okay, some questions?
Just the slide before, is there any optimum value for alpha to not have this change in topology?
Change in topology?
Yeah, I mean, between left to...
So to suppress, I think what he means is to suppress the fingers. Is there some optimal value for alpha for the taper?
Yeah, so there is a specific value which you can kind of approximate from linear stability, where basically if alpha is less than a value, you'll see maybe partially suppressed fingering, but once it becomes greater than that value, then it's completely suppressed, yeah.
So the choice of coupling F here, there are probably some choices you can make for the level set method, or is there just one canonical way to do it?
The choice of phi?
Yes,
The canonical way is to use a signed distance function. Yeah. But technically, you could choose anything that is positive inside the bubble and negative outside the bubble, but you typically choose a signed distance function.
Okay, great. Thanks very much. Let's thank the speaker.
Yes, hello. Sorry about my call. I think the North and the dinner yesterday are trying to get the better out of me. Anyway, we carry on. Today we're going to speak about direct numerical simulations of annular flows. These are countercurrent simulations, and the specific emphasis here is the presence of the so-called flooding phenomena, and we also would like to see what happens if we add surfactants to such flows. So why is this industrially relevant? These flows are observed in many industries, fast-moving consumer goods, oil and gas I've mentioned here, like transport of hydrocarbons through risers. The presence of surfactants in such systems in the oil and gas is very interesting from an enhanced oil recovery perspective. From a safety standpoint, the nuclear industry has a lot of interest in such flows as well. Now, from a research perspective, a lot of work has been done in the past experimentally. A lot of work at Imperial College. You might recognize some of the names here. Professor Jeff Hewitt's group and elsewhere. Recently, Zadrazil published a very good paper on co-current annular flows, where he gave a lot of stats and a lot of theory behind why we have the formation of droplets in certain waves. From a CFD perspective, on the other hand, not a lot has been done in the 3D computational domain. A lot of the work is primarily 2D. So there is a need to investigate these flows further in a 3D domain. So what we are going to use to simulate such flows is a code which is essentially a hybrid code. It's a level set and a front tracking code. Now this is very good when we speak about surfactants, because as you see, there's a certain equation that needs to be resolved at the interface, and having the information of the interface through the front tracking code gives us the ability to solve additional equations on the interface. The one other thing about this code is massively parallel, so you see some of the simulations are quite large here. So one of the first setups that we looked at was a more classical setup. It's the falling film. A lot of work has been done since the Kapitsa father and son started their experiments. So this is a bit of a twist on the geometry that's more classical. It's a circular angular geometry. The simulations are very high resolution. So this is our vague attempt to try and join the billionaires club, as was mentioned yesterday. So these simulations actually have about 220 million cells in them. What's interesting about these simulations is the use of a periodic domain in the streamwise direction. Now, this allows us, the use of a periodic domain obviously allows us to focus on, a specific area of the flow, basically savoring the resolution where it matters. What we're trying with these simulations is we're trying to validate the code, and we are trying to validate it against the experimental data by Zdrassil. So the film thicknesses that you see here, which correspond to these Reynolds numbers, basically are a direct comparison to that paper. Now, what we observe from wave dynamics perspective initially is qualitative in agreement with what we see in theory. So at low Reynolds number, you see the formation of these capillary ripples. As we increase the Reynolds number, we do see the formation of these gravity capillary instabilities, which come in the form of small substrate waves. And as the Reynolds number increases, the capillary ripples diminish, and we see these very large, long, shear type waves. Now, this is just a qualitative comparison. At this stage, we'll be doing a more statistical analysis as we go forward of these simulations. Now, a bit of quantitative validation on these flows. We did a little bit of work on the velocity profile. So we took a number of probes spatially and time-wise, and we compare them to the average velocity profiles that are given in the Zdrassil paper, and we see that actually we have a very good validation. So we are definitely on the right track here. Now, moving on, I promised to you that we're going to speak about the flooding phenomena. Now, because these simulations are very large and they take a very long time, as you might expect, we took a step back, and so we went to lower resolution simulations. Once again, we do use a periodic domain, so we can make use of the cells more wisely. And one thing here is, so we have a liquid film that's initialized on the side of our pipe. And then we have, in the core of our domain, we have a pressure-driven gas flow, which is driven via body force, which is a very standard way of dealing with periodic boundary conditions and driven flow. Now, what we observe, once again, qualitatively, is very promising. So at low Reynolds numbers for the gas and the liquid, we don't see any entrainment of the liquid phase. What we see is the formation of these ripple waves, which decay over time and disappear. As we increase the gas flow further, we do see the formation of ligaments and the entrainment of droplets. Things become very exciting. As we go further up the Reynolds number for the gas, here we're about 15,000 Reynolds number for the gas. We see a complete flow reversal of the flow, and we see wave structures which are very much in line with what theory has suggested thus far. And as we increase the Reynolds liquid number and the gas Reynolds number, we enter into the so-called churn flow regime, where things are very exciting, and I'll show you a video of this flow regime earlier. So thus far we have a very good qualitative agreement with what's in literature. Now here I will show you the first simulation. Actually, I won't show you this one because we don't have much time. So I'll show you this one, which is a lot more exciting. You basically see all the flow features that are inherent to the flooding scenario as well. So you see the formation of ligaments. You see the formation of droplets here. What you also see is liquid bridges, which is also something that's been observed before with these flows. So once again, here on this slide, you see the ligament, you see the droplet, and you see the liquid bridge. This took a very long time to adjust, so it's everything on one slide as well. So it's very nice. Right, so one thing I promised as well was to speak about surfactants. Some of you might have attended the exciting talk by Professor Stephen Wilson on Tuesday, and he spoke about anti-surfactants. This is the more classical notation of the convective diffusion equations that we are trying to solve. If I can bring your attention here, there's a source term, which is what governs the exchange between the surfactant species, between the interface and the bulk. And we also use a Langmuir model to determine the local surface tension. Now, what happens when we add surfactants to our flow? So we added surfactants to the downward annular regime, where we don't have the entrainment of any droplets. And what we saw is a somewhat rigidification of the film itself. We see less peaks being detected by our algorithm. You see, we see the average wave amplitude decreasing as well. So what we accredit this to is, of course, the appearance of surface tension gradients and the Marangoni effect. So what happens if we add surfactants to the flooding regime? So this is a video from the lab. On the right here, we have surfactants. So what you see is the creation of much finer, almost misty droplets, misty flow appearing in the presence of surfactants. What we accredit this to is the so-called tip streaming phenomena. Now, this is basically the phenomena where you have surfactant species being entrapped on the crest of the waves. And due to a more energy favorable situation, the droplet starts detaching, and they're much smaller in size. If we run a quick analysis on the droplets that we see, what happens is we do see that in the presence of surfactants, we have the creation of these much finer droplets. Thank you very much. So this is my summary slide. I'm just going to leave it here, and I'm going to show you another very nice simulation of the falling film on the right here. So thank you.
Can you just elaborate a little bit on how exactly you implemented the surface transport equation? You said it was important to have the scheme the way you did, but then you didn't.
Yes, so if we look back, so what I wanted to highlight here is, so we have two governing equations. One is for the concentration in the bulk, and the other one is for the concentration of surfactant species on the interface. And then we have a source term. So in some cases, we know that some surfactants are soluble, some are insoluble. And then basically we have this source term that governs the exchange. And there are some parameters in there.
Sure, but how did you discretize that equation on the surface?
We use the front tracking codes.
Okay.
Yes.
So I can start talking because we all seen Liam's talk already. So we've seen the phenomenal viscous fingering. Hopefully we'll see it on the screen soon. What happened? Okay. sign. No, that's... This is not the first time it's happening to me. So the last time was 10 minutes at the APS, and I lost 3.
I know you did test it earlier. I was
Yeah, it worked. And it's the same story at the APS, exactly the same.
Do you want to start telling us roughly?
Okay, so Liam was telling us about viscous fingering. And so when you inject a less viscous fluid, for example, air in our experiment, into a more viscous fluid, we use silicone oil, between 2 parallel plates, and with a small gap in between, you get this instability called viscous fingers. So I'm going to tell you a twist on that story, what happens if you replace the top plate with the elastic sheet. Still no sign of the... I don't know, should I rotate my screen and just show you? Turn it around. Okay, so imagine a blister, basically. This is what happens. If you're injecting fluids below elastic sheets, that you create a blister-like shape, okay? So everyone can imagine blisters on their feet. And what that does to the fingering instability, it suppresses it in certain regimes. And if you start injecting at higher injection rates, that does lead to instability, but the instability is modified. So you no longer see these fingers that sort of extend all the way to the injection point, like in Liam's talk, but they actually are close to the interface. So I'm going to kind of hopefully tell you about, or not, tell you about what sets those fingering patterns under elastic sheet. Maybe not. That's not my talk. That's a different one. Oh, maybe I can just draw it with a pen. Something's up. Okay. So if you would see Liam's talk, we get these fingers, which are big, right, and go all the way to injection point. It's the top view of the experiment. The fingers under elastic sheet look differently. So if this is an interface, on average, then the fingers are very short and stubby and near that interface. So the question is, why is this so? And what can we say about the patterns? Okay, so that's kind of, okay, so let me flip through. So what's important to note here, then when you have an elastic sheet, you're also inflating it as you inject fluids. And then basically ahead of that inflation, the interface, so these are instantaneous shapes of the sheet as you inflate the top sheet and inject fluids. And ahead of the interface between 2 fluids, there is a whole region of viscous flow, which kind of the interface sees, and this region forms a wedge. So that's something that I want you to remember as I move on. And this is what happens basically when you do see fingering. So on this side, we're looking at the rigid cell, and this is what happens if you inject below at the high enough rate below the elastic sheet. You get these fingers, but they're short and stubby and near the interface. So I'm going to hopefully tell you how these are formed. So in order to model the system, we coupled those lubrication equations that Liam has already showed us to the equations that describe what elastic sheet is doing. And the main difference between the classical system is that you have now the local gap thickness that can change in response to sheet deformation, and vice versa, that in turn changes the sheet deformation. So it's really a coupled system. And then we have some conditions at the interface, and Liam has already mentioned them. I should just say that we also modify our conditions to get quantitative agreement with the experiment and account for the fact that the classical lubrication equation assume this, but actual transverse cross-section of the system looks like this. So you have a curved bubble, and you have some wetting films left on top and bottom of your cell. Okay, so we're going to do the classical thing and compare linear stability analysis with the experiments. So the take-home message here is that the base flow in our system is inherently time-dependent because we have radial geometry, and that's only exacerbated by the presence of the elastic wall. And then we perturb that non-axisymmetrically. And then sort of we look at this quantity. So this is a measure of fingering instability. It's this instantaneous growth rate in our system. So if this quantity is positive, you have instability growing. If that quantity is negative, it's suppressed. We also compare that to the experiments. Here is a typical instantaneous pattern that we see experimentally. And if we look at the sort of shapes of fingers, then you can see that they vary a lot along the circumference. So we have to plot sort of the amplitude of the finger as a function of sort of average radius, and you can see that initially instability grows, reaches our maximum, and then decays. So our instability, by the very nature of the problem, is transient, and given sufficiently large cell, everything would decay eventually. So there is a lot of variability within the same experiment. There is also a lot of variability if we are to repeat the same experiment many times, so the same values of parameter. And so that's reflected in this next plot. So here we're looking at the growth rate as a function of sort of the wave number. And the dots are experiments. The solid lines are linear stability analysis. The linear stability analysis predicts one wave number to be the maximum one. The experiments don't agree very well if you're at small radii, and then different curves correspond to different radii. If you move away from the injection point, eventually the agreement between theory and experiments is better. This is also illustrated here. So this is now the growth rate is a function of the point point at which the average interface is. And initially, so these are experiments. This is linear stability analysis. You can see that linear stability analysis always provides an upper bound on the growth rate observed experimentally. If we do lots of experiments in different cells, then we've done these by increasing sheet thickness, thereby changing the bending modulus of our sheets, by changing the initial gap of our cell, by changing fluids and sheets used all together. And what's consistent as we vary injection rates is that the linear stability analysis, which is shown in solid line here, compares relatively well with the experiments at lower injection rates. And then later on, you see that the growth rates predicted by linear stability analysis are way too big, basically. And then the experiments are sort of below what's predicted by the theory. So that's to be expected because by here, the nonlinear growth rate kicks in. Okay, so at lower injection rates, we have good agreement. But that's sort of comparing directly the growth rates. What about the wave numbers? So if we look at the patterns, we can see that there is, depending on what kind of cell we're using, there are different wave numbers observed in the cell. And so what we did in this plot, we compared the wave number, or the number of fingers observed experimentally, with the number of fingers predicted in the linear stability analysis before the whole system starts decaying and before this instability starts decaying in that kind of, if you remember, the thought of the amplitude as a function of time. So what you can see here is even though our growth rates are only working in the linear regime, we actually can predict the number of fingers very well throughout the experiment. So the linear stability analysis is very good at predicting the number of fingers observed, and therefore we believe that the wave number is set by the linear instability in the system. Finally, I want to say what happens. So earlier I told you there is this region of wedge that you should remember ahead of the interface. And that region seems to be correlated with the depth of the fingers. So if, again, we look at the patterns, in particular this one and this one, you can see that there is a notable difference between the amplitude of fingers observed in nonlinear regime. And clearly here, fingers are a lot less deep than there are in this figure, for example. And so what we did is, for all our experiments, we compared the amplitude of fingers with the size of the wedge. And so our experiments are with dots, shown with dots, and the gray region is sort of length of the wedge predicted theoretically. And you can see that over the whole range of experiments performed, we have a very good correlation between the two. So in other words, in order to predict how deep your fingers are going to be, you have to just compare it to the size of your wedge in your system. Okay, so let me just conclude by saying we have a lubrication model. This seems to be in a quantitative agreement with experiments. Fingering in this system is overall transient, but when it's there, we can predict the number of fingers, and it's at the linear instability stage, and we have depth of fingers that correlates with the wedge length. So by finding the wedge length, we can find the depth of the fingers. Thank you.
Any questions?
Sorry, I'm experimentalist, so I can't understand the long equations that you have. But if you want to translate your equations into a more physical, tangible thing, if we think about the wedge surface that you have here, that's the first time that I saw it on a log because I'm working on this a lot. So the main issue I have here is how you say this wedge.
So it's a wedge of liquid, basically. How do we? Yes.
How does your stiffness affect that finger formation?
How does it affect? So there is a length scale. So I'm trying to claim here there's a length scale in the system, which is given by this wedge, where basically main flow happens, and that length scale essentially sets the length of the fingers.
Okay.
So that's kind of
good enough.
Hi, my name is Ghanem Al-Jawish. I'm a PhD student at Keele University. My supervisor, Shalish Naiz. I'm going to talk about spreading of cooling drop. Here, I want to look about the spreading and extending of the lava. Then we see here the dome it's want to extend and spreading. The main motivation in this model is to understand the dynamic behind the spreading and extending, which is very important. And another motivation in this slide, which is we want to know how the front of the edge of the dome it's breaking up to fingers. As a lava dome, the main force, which is the gravity, makes the spreading, and another there is the motion liquid flow is very important. There is many applications about that, and also the non-external cooling effects are important, for especially in the low lava dome. The main focus in my project is to understand the spreading behavior, including non-external effect, and also the coupling between the flow and the temperature by the temperature-dependent viscosity, and also understanding the fingering stability to near contact line, which is not mentioned here. The goal is to get better theoretical understanding of spreading dynamic. In this model, we have a hot liquid dome spreading by the gravity on an inclined plane persuaded by thin liquid film, and also there is source coming from the vent. The interesting thing is we want to see how to get the evolution equation represented by the edge of x, y, t. We use the Navier-Stokes equation and the evolution equation to model the flow as a Newtonian, and the temperature evolution equation, and the coupling between the temperature and the flow using visco, temperature-dependent visco. The phase transition effect, it's not consist here, and we use the replication theory to derive the evolution equation in 1D film thickness h and 2D temperature theta. And we use the numerical solution to explore the spreading dynamic. Here some relevant literature. There is many work in the Newtonian one and isotomal part, and some work in isotomal non-Newtonian, and a few work in non-isotomal. We follow the Banfield paper, including more statistics. Here, we want to represent the evolution equation of one thin film and the temperature. H is given by the flux, and W, which is the source. The flux is determined by the horizontal gravity and vertical gravity. This contribution coming from the variation of viscosity in Z direction. And also, the temperature changing by the theta changing by the temperature. The second and the third theorem, which is the convection theorem, and the last theorem, that one, which is the diffusion theorem. U and W, which is flow speed, is changing by the Z and X direction. Here, temperature, which is temperature component, TA, ambient temperature, and TE, which is source temperature or evolution temperature. And we use the viscosity as exponential decay in theta. Alpha is constant. And the WS, which is the source term, use it as a Poiseuille flow. W dot is source strength, and X star, which is the source radial. We use two boundary conditions. First one in Z equal to H, which is in free surface, a component from A, which is the heat transfer coefficient, and the other condition in substrate Z equal to 0, which is component from the Peckley number and the source, and the B, which is also heat transfer coefficient. And also we used initial condition, which is used as a parabolic drop shape. And also we have condition in x-axis, which is H goes to B1 and theta goes to 0. The main parameter we have is Peckley number, which is compares conductive to diffusion heat transfer, and also AB, which is heat transfer coefficient. In this slide, we show the result for varying Peckley number without source. We see we try to compare between isotomal and non-isotomal varying the Peckley number, fixing the other parameter. We see for the small Peckley number, the diffusion term is dominated in the early time, and after that, the diffusion term is dominating, and the shape is look like isotomal 1. But for a large Peckley number, the diffusion term is dominating for the whole time, and we see the hump is start growing. This will be clear for the next slide. Here we have, we use the theta and the H without source varying Peckley number and fixing the other parameter with a different time. In the first column, we see for a very small Peckley number, the temperature is dropped to 0 very quickly, and the diffusion term is dominated. And the shape in the final will look like the same of isotomal 1. The other column, we see the temperature is not going down faster. It takes some time, and then but finally also take the same of isotomal shape, but for a little bit not quicker than the smaller Peckley number. But for the large Peckley number, we see that diffusion term is dominating, and the temperature is varying by the Z direction, and there is a cooler region in the front. This cooler region tries to vary the flow to flow, and then the hot flow behind the cooler region, they try to over the cold region and making the hump. This hump will be very clear in the next slide. In this slide, I'm varying the heat transfer coefficient and fixing the Peckley number for a large Peckley number with using some source and for different value of different times. In the first column, we see it looks like vertical isotomal, and the cooling region, it's not much. And the hot liquid here, we reheated the cooler region. But for some big value of heat transfer coefficient, we see the cooler region is going more stronger than the smaller one. and the heat will, and the hot liquid, they bend here and they try to push it and reheat it. That's make a little bit harm here. But for the high heat transfer coefficient, we see the hump is start growing and appearing very well, and the hot liquid and behind the collar region is start to push it and to get over the collar region, making very growing the hump. This is for a long time. It starts growing. It's depending about how the source, strength of the source. If we use the more than 0.5 the source, the hump is going more than this part. Conclusion. We use a very small Pickley number and large Pickley number. The large Pickley number is look like also the acetominal spread, but with lower viscosity. And we also mentioned about the intermediate Pickley number. We get two features in this part, which is fluid hump with near leading the edges without source. And also, we use the growing fluid hump near the leading edge, but with the high value of heat transfer coefficient. And also, we got the insulating hot region surrounded by the collar layer, but we don't show it here. We try to investigate transition stability of a flow feature to getting fingering stability. And also, we use the realistic variation viscosity with the temperature, for example, bioviscosity model. And also, we included phase transition effect. Thank you.
Maybe time for a quick question.
Yeah. You mentioned you work on 1D and 2D. Is there any scenario for 3-dimension?
Yeah, I'm working for 3-dimension, which is used by contour. Also, we use it here, the 2-dimension. Also, we use it the contour plotting. And I'm working for 3-dimension to show the fingers and the hump is very well.
Okay, thanks very much.
Okay, so this is really Callum Cuttle's work, who's a PhD student with Draga and myself, but couldn't be here. So we're looking at, so if you take a rigid Healy-Shorr cell, that's a classical problem by Safman and Taylor, and you displace a viscous liquid by a less viscous fluid, such as air, then you typically see a single mode of propagation. And really what you have there is that airflow is competing against viscous and capillary forces to displace, to create this flow. Now you can do the same same experiment, but you can replace the top boundary with an elastic sheet, and if you such as in the cross section shown there, and now you have air competing against viscous, capillary, and elastic forces. And in that case, if you have a flush sheet, you will see pretty much exactly the same as you see in the Safman-Taylor problem, single mode of propagation. So, but many things have changed. Really, because you're inflating your cell, you now have a sheet profile that looks something like this, and with interface here at 0. And you're no longer displacing all the fluid in the channel. You have quiescent fluid ahead, and you only have fluid motion in a small region ahead of the air finger. The motivation for this type of work came originally from pulmonary airway reopening. So if you think of the first breath scenario of an infant, then you have airways that are flexible, they're occluded by liquid, and they collapse, quite strongly collapsed, and must be reopened by the first breath of the infant. So if you take a sort of idealized elastic tube, it will collapse in this two-mode configuration, and you really have quite large variations in the depth of the channel. So it's a very irregular channel. And so really the object here is to look at the effect of membrane collapse in our very simplified channel geometry on the type of finger propagation that you get. So a lot is known about the mechanics of airway reopening, and I just want to highlight two features that are of interest to me here. So first of all, if you look at the bubble pressure, the propagating bubble versus capillary number, then you have a peeling and pushing branch. Many people have found this in 2D models, and here I'm showing some 3D simulations. Now, the peeling mode is one where the bubble is very close to, there's very little fluid ahead of the bubble. The pushing mode is typically characterized, so that's the mode where elastic forces are more important, and the pushing mode is one where there's quite a lot of fluid ahead of the finger, and viscous forces are more important. Here we parameterize the motion of the bubble with a capillary number, and that's effectively in our experiment fairly closely related to the flow rate we inject with. The other feature I want to show is this one. It's a very interesting phenomenon that goes on when you place yourself close to the bottom of the pushing peeling branch at the junction between the two, and you have unstable behavior. And that's Halpin and et al., and including Oliver Jensen, who's here, who looked at this problem in a 2D system. And the 2D system is effectively a bit like that, schematically, where you're looking in from the side. And so there's no feature, no finger as such, but you're only looking at the transverse or depth-wise dynamics. So they found that the pushing mode was unstable, and they found non-periodic large amplitude relaxation oscillation between pushing and peeling. Okay, so our experiment is effectively a 60 centimeter long Heeler short channel with a thin elastic membrane or sheet on top. And the key point that I want to mention about it is that it's a very difficult experiment to set up, because you're trying to effectively, you apply pre-stress to the membrane, and you're trying to get extremely regular stress distribution in your membrane over 60 centimeters. And it's a difficult thing to do, but basically the level to which we're able to control it is that when we propagate a stable finger in that channel, we have about 20 Pascal pressure variations. I can't feel 100 pascals on my finger. So it's very, very well-controlled pressures. Okay, so we collapse the channel, and all you need to know is that I'm going to look at this sort of level of collapse of the orange curve here. So when you only have a very thin film in the middle of the cross-section and quite thicker films on the sides. We're looking from the top, and typically we'll see fingers moving, and I'm not going to show you lots of moving, I'm going to show you time-lapse images. So it'll be something like this. So I'm going to show you a whole series of these time-lapse images. Okay, so if we start by just increasing the capillary number from a low capillary number to, we find two types of peeling modes in our system. So what I should say is, before I said that there's only one mode of propagation, say in the 3D simulation, but in that case, they impose symmetry, and they only look at steady states. So here we do the experiment in a slightly different geometry, but this is what we find. So we find, initially, we have, so the top sequence is an asymmetric mode, as it happens, but initially stable, and then it goes unstable to tip splitting as you increase the capillary number. And the second mode is what we call, is a mode that is effectively where the tip is unstable to very small scale fingering and of small amplitude. So why do we find these unstable modes in the first place? Well, really the devil here is in the underlying flow, and that's not something that we understand or that is that easy to describe. But effectively, as you increase the level of collapse in your system, your finger broadens, and as it broadens, effectively the tip curvature reduces, you get a flatter tip, and therefore it becomes prone to fingering instability, or very much of the Safman-Taylor type. This tip instability comes therefore in two flavors here, and it's consistent again with viscous fingering. Low capillary number, you have larger wave lengths, and larger capillary number, you have smaller wavelengths. And what we observe really is that what's crucial here is on which side of the inflection of the sheet the interface sits. And that's something that we don't actually understand, which I think is kind of interesting, is if you have enough fluid ahead of your finger, you get the green mode at the top, which is very much like tip splitting in a linear rigid channel. And if you have now the interface pointing beyond the point of inflection of a sheet with less fluid ahead of it, you get the small-scale fingering. And that, because we studied that a lot, I can tell you with some degree of certainty that it's really very analogous to the fingering due to peeling of an adhesive tape, so the classic study of McEwen and Taylor. Okay, so how do we go between these two modes? Well, we get a pushing mode. And I believe I've certainly never seen a pushing mode in these systems, and the reason is because it's unstable. And it has, if you look at the average pressure of your visualization window as a function of the capillary number, you have your asymmetric peeling and your symmetric peeling. And then in between, you have this pushing branch. And the pushing branch, in all that region, there's effectively unstable behavior where you're switching between modes. So you are effectively, in the experiment, only looking very transiently at certain, if you like, solutions of the system. So you find you pushing and peeling to an extent, and then instead of just looking at the average pressure over the visualization window, you can look at the instantaneous pressure, and therefore you can look at how the pressure capillary system evolves. So how the system evolves transiently in the parameter plane. And effectively, you have here what looks very much like cycles. And in the experiment, what you have is you only have one cycle, and then the system goes off. And this is very reminiscent to some of these peeling pushing behaviors that were seen in the 2D model. And there's some, okay, so that was seen in the 3D model. And so you can look a bit more closely at these things, and you have a whole lot of different sort of transient modes that develop. And so really the key feature here is that we are imposing constant flow rate in the experiment, and as a result, the finger can choose its pressure and its capillary number. So these are really two independent parameters or two independent variables in the system. If you go from pushing, so you have a whole load of different scenarios. Pushing asymmetric, you start near sort of on the pushing mode, the pointed mode. You go off to asymmetric, you go off to pushing again, and etc. There's a whole series of these different modes, and it looks kind of like this. And here the pressure fluctuations are no longer 20 Pascal, but they're around 100 Pascal. Why we only ever get one cycle is that what it looks like is that the pointed pushing mode evolves via, say, the asymmetric mode, and then it gets more pointed. And when it gets sufficiently pointed, it goes unstable to fingering, and it shoots off towards the sort of peeling branch. Okay, so let me conclude. So we've looked at a whole host of different sort of fingering modes in an elastorigid channel. This system keeps on surprising me because it's extremely rich. We are, in parallel, running a 2D depth average model investigation of this type of system. And really, the bigger picture for us at the moment is that we're looking for why front propagation becomes disordered in general, and thinking that looking at all these multiple solutions that have emerged and keep on emerging in this system will give us some nonlinear dynamics clue as how fronts go unstable. Thank you very much.
Thanks very much.
Okay, that's an updated title. That's my motivation. Yeah, I just let you read it. It's fairly straightforward, some industrial applications, but also a beautiful piece of fluid dynamics. There is actually a big difference between vertical and oblique curtains because of curvature of the flow. They're actually more like jets, and the jets were explored to a great extent. They used to deal with curvature. They introduced a certain collinear set of coordinates, and they assumed that it was orthogonal. But it actually was not. And people knew about that even before this work was published. But actually, unsurprisingly, the final equations derived by Walk and Dyson turned out to be still correct, because for slender jets, curvature non-orthogonality is actually asymptotically small. So that's the setting I'm going to consider. In this case, the flow goes up and down, but it can go down, and we'll see. So 2h is the width of the outlet. I'm going to use curvilinear coordinates associated with the central line of the jet. L is the length along streamlines, streamwise coordinate, and tau is the cross-stream coordinate. But the difference with the previous work is that I do want to use an orthogonal coordinate system. And I force it to be orthogonal just by making it orthogonal. I am looking for the coordinates as I'm going. In fact, I didn't have to do it in the two-dimensional problem which I'm going to talk about, but in view of stability analysis, which I'm going to perform as well, in this case, I will have to use this trick. 3 non-dimensional parameters. Just take a look at them. You will probably recognize some of them. Epsilon is the reciprocal of the Froude number, but what's important, it's also the slenderness parameter. And the other two are the reciprocal of the reduced Reynolds number. Reduced, it means that the actual Reynolds number multiplied by the slenderness parameter, and the reciprocal of the Weber number. I assume epsilon to be small, slender curtains, but these guys can be anything. Scaling actually is pretty tricky here. Well, this part is not tricky, but the next one is. Just read it. I explain what the problem is. The problem arises only for non-stationary curtains. If they oscillate, well, normally you would have streamwise velocity much larger than the cross-stream. But since the curtain can oscillate, and it actually can be pretty violent, to leading order, the scalings of the two velocities coincide. What you have to do is you have to calculate the motion of the curtain using those curvilinear coordinates and subtract them from the actual velocity. And the rest of them, the rest of the cross-stream velocity is going to be small. The rest of it is, again, straightforward. It's much more convenient to speak in terms of the angle of the curtain between the curtain and the horizontal. Positive alpha, curtain goes up. Negative alpha, curtain goes down. These are the asymptotic equations. That's the streamwise equation. That's the cross-stream equation. Well, that you recognize. To understand what the terms in these equations are, that's gravity. We are using a non-inertial coordinate system. So there must be forces of inertia. These are the forces of inertia. X and Z, they are coordinates of the Cartesian coordinates of the curtain, depending on tau and L, the curvilinear coordinates. But apart from linear motion, you also have local rotation. So there must be a Coriolis force. The alpha, the L, the alpha, the T is the angular velocity of local rotation. And of course, you have the centripetal acceleration or centrifugal force, if you like. The alpha, the L is the curvature. The rest is standard, and observe there is no pressure in the streamwise equation. It's actually asymptotically small. The steady solution is just the same set of equations as before, except I eliminated the pressure. You can eliminate the pressure, and that's the streamwise equation. It links the curvature of the flow, surface tension, centrifugal force, thickness of the curtain, tau plus, tau minus. Essentially, this is the thickness of the curtain, and gravity. And that's where surprise is coming. Let's consider sufficiently strong surface tension. This is positive. Alpha is between -0.2 plus 0.2 positive. So if all of this is positive, the alpha, the L is also positive. What does it mean? It means that the curtain goes up. Well, that's a bit of exaggeration. It bends upwards. But actually, I've considered two limiting cases. And in both cases, you can actually show that not only it bends upwards, but it actually eventually goes upwards. It's completely counterintuitive, but that's what it is. It reaches to the height where the initial supply of kinetic energy can take it, and then it probably splashes just down because the width becomes very large. But similar solutions, you can find them for jets. And these equations I did not derive. I just took the equations of Wolbach and Decent. I just, they reduced it to my case, and there is such a solution, but of course it's unstable because the jets, they have cylindrical structure and violently unstable. So that's the dimensional version of the condition when the curtain goes up. And then you can see that this part, except the half, it's actually the flux of the momentum through the outlet. It must mean something physically. I just can't figure out what it is. But what's important, that an experimentalist can easily make an experiment. Well, probably not easily to the experimentalist, but to me it looks easy because you can just decrease h sufficiently. I have time, surprisingly, so I'll show you some examples. That's highly viscous liquid. The threshold value of gamma is 1 here, so this is just a parabola. If you throw something, it goes down along a parabola, which is the same parabola. But then these things in the circles, the surface tension, it becomes steeper, and then when gamma is greater than 1, it goes up. Everything non-dimensional, so they reach exactly the same height. And that's the comparison of highly viscous and nearly ideal liquid. With these guys, this is a parabola, but this is not quite a parabola, and ideal liquid goes a little bit further than the viscous one, which is not surprising. The big difference is here. This point is the original height. It's the place where a first stagnation point occurs in the flow. And with ideal liquid, it is known that it is unstable when a stagnation point appears. So clearly, ideal liquid can't go up. So with the viscous can go all the way up. Okay, that's finished.
Okay, any questions?
Yes.
Just go back to the previous slide.
Sure.
What I want to ask about is what happens when the surface tension is 1?
Is 1, it goes, it bends either immediately down or immediately up.
But I can't see how it smoothly goes from...
No, it cannot. A singular point. Well, it means that I have to go to higher order in my equations and collect some smaller terms, otherwise it's division by 0.
But it's not a coordinate singularity to do with the fact that...
No, it's not. A coordinate system are all okay.
Thanks.
they're conformal.
No, then let's thank Eugene one more time.
Thank you. So this project is I'm collaborating with Alice and Andrew. We're working on the mathematical side of this problem, whilst Anne and Gregoire are in the laboratory working on the experiments. Before I give some motivation about why we're studying this problem, here is the Healy. We've heard a lot about different Healy-Shaw cells today. This is the situation I'm dealing with. So we've got a rigid rectangular channel. It's very long compared to its height, and inside is filled with a viscous fluid. We've perturbed the cells slightly in the form of a rectangular occlusion along the bottom floor of the channel. We form a bubble on one end of the, or an air finger, on one end of the channel, and then the fluid is extracted at a constant flow rate. And what we're interested in is the pattern formation of the bubble or the air finger. We've seen these the pictures on the right before from Anne's talk. What's interesting is that below a certain flow rate, an air finger will propagate in a steady manner, as can be seen by figure C. Above a certain flow rate, we get disordered pattern propagation characterized by multiple tips forming. Now compare this to another type of canonical flow in a Poiseuille flow, where below a certain Reynolds number, the flow is laminar. Above a certain critical Reynolds number, the flow becomes turbulent. This transition to turbulence, using dynamical systems theory, can be seen as a meandering between the stable manifolds of weakly unstable edge states of the system. And the broad aim of this project is to see if we can extend the ideas learned in Poiseuille flow and in the transition to turbulence into that of the Saffman-Taylor fingers and finite air bubbles. What I'm going to talk about today is some preliminary results which we've found looking at the dynamics of a finite air bubble. So recent experimental work done in Manchester has shown that below a certain flow rate, so Q is the flow rate, below a certain flow rate, bubbles propagate in a steady asymmetric manner, as could be seen by the yellow region. As we increase the flow rate, the bubble propagation becomes increasingly disordered, characterized by a different number of tips forming as the bubble propagates through the channel. So our first goal is to see if our mathematical model will replicate this qualitative behavior. So these are the equations which we're solving. We solve a similar equation to Scott in his talk earlier for the bulk pressure. The presence of the occlusion is contained in the B cubed term. On the interface, we demand that the dynamic condition and the kinematic condition is satisfied. We also have two additional constraints. We demand that the volume is constant in the bubble, and that will give us the bubble pressure as part of the solution. We also demand that we're going to be traveling in a frame of reference with the bubble, and that will give us the speed of propagation of the bubble. So here we have two slightly different initial conditions. The bubble on the left is slightly asymmetric and slightly different eccentricities. And we can see as we time integrate this, this initial condition, we can see we get two very different types of behavior. On the left, we get 3 tips, and on the right, we get the 4 tips. So qualitatively, this is encouraging because it appears to match with what the experiments predict. In addition to this, if we start with quite an elongated bubble, we're actually able, and time integrate forwards, we're actually able to also find, on a much larger time scale, oscillatory solutions, where the bubble appears to oscillate above the occlusion, something which wasn't captured in that experimental picture. So what we find is that we have two basic modes of propagation. One of the modes will lead to breakup, and the other one is oscillatory. And it appears to be very sensitive to the initial conditions in terms of the eccentricity of the bubble and the level of asymmetry of the initial bubble. So in trying to understand that, we are going to do a parameter study on the steady solutions. We're going to use the flow speed as the control parameter, and we're going to use the speed of the bubble as a solution measure. What we find is a very interesting bifurcation structure. For low flow speeds, we find that there is a single steady asymmetric branch. So the dashed lines indicate unstable solutions. As we increase the flow rates, we find that the S1 branch will stabilize via a Hopf bifurcation, given by H1. And at that point, we have two stable solutions, one asymmetric and one symmetric in the S2 branch. As the flow rate increases, we eventually approach a pitchfork bifurcation. And here, the stable symmetric solution will branch out into an unstable symmetric solution and two asymmetric stable solutions. Eventually, this second, the AS2 branch, will destabilize via another Hopf bifurcation. So what we end up with is this bistable zone. What's curious is there's quite a lot of things happening in very small bandwidth of the Q parameter space. In fact, this diagram is for a fixed volume and a fixed height of the occlusion. If we change the volume and we track the location of the Hopfs, we find that the first Hopf is very robust to changes in the volume. It appears to be independent of the volume of the bubble. Something intrinsic is happening there in the system. So we're curious to know what happens either side of this Hopf, because this may, obviously, with a Hopf bifurcation, we get periodic orbits emanating from these. So if we start off on the slightly unstable side of the Hopf, so we start off with this stable solution, and we're going to perturb it by its complex eigenmode. Now we're free to choose the phase of that complex eigenmode, so I've chosen two different phases. And what's interesting, as we time evolve the bubble, we get two very different types of behavior. On the left, we get a bubble which will lead to breakup with two tips, but on the right, the bubble will transiently evolve to the stable asymmetric state. If we look on the stable side of the Hopf, a similar thing happens, where we choose two different phases to perturb the steady solution. And as we time evolve, again, we find on the left that the solution appears to, as predicted by the linear theory at least, oscillates slowly towards the stable solution, while on the right, we same eigenmode, same size of perturbation, we end up with bubble breakup, and a two-tip solution is formed. We can nudge it even a little bit harder, and we find that there's some really interesting dynamics, and before it eventually ends up at the asymmetric state. We can see that, and this takes a long time, we can see this more clearly, these complicated transients, by looking at a projected phase plane. So here on the left, we are using the bubble pressure, which comes as part of the solution, and the speed of propagation as the vertical axis. And you can see we're starting off at the S2 solution. There's this very interesting oscillatory behavior, transient behavior, before it eventually ends up to the asymmetric branch. If we look at the time signal for the speed propagation, the figure on the right, we can see that even though this solution is linearly stable, we can see that there's clearly some kind of transient nonlinearities which is causing this bubble to go to the to become unstable and go to the stable asymmetric state. So what we found in this preliminary investigation is that we've got some highly complex time-dependent behavior. There's a question as to can we quantify whether breakup happens or whether it's oscillatory. And is it possible to determine it in advance? There's clearly some property of the eigenmodes which will help us determine this. we're currently working on a weekly nonlinear stability analysis. We'll get a lot of stuff for free by analysing the weekly nonlinear dynamics near the Hopf bifurcations. We'll be able to find good initial guesses for the limit cycles. We'll be able to determine the criticality. And also, hopefully, we'll be able to get some kind of quantify which eigenmodes will cause this breakup. Yep, that's what I just said. And I should just say that solutions are brought to you. The solutions were solved using the finite element method, open source library, UMFLIB, developed here in Manchester. Thank you.
Excellent stuff. Any questions?
I got one. Okay, I couldn't quite tell, but from your computations on the unstable side of the Hopf bifurcation, those weren't heading towards the limit cycle, is that right? They were either breaking up or heading to...
It could be. I don't believe it is, because let's go back to the...
So the follow-up question is then, does that mean you expect they're going to be subcritical bifurcations?
Yes, exactly. Yeah, you've answered my question. Yeah. Yeah, we strongly believe there's going to be subcritical, so the limit cycles are going to be unstable. And
there are stable limit cycles?
Yeah, there are. So I haven't had time. So we believe H2 is supercritical, for example, and we do find stable limit cycles around there. Yeah, so yeah.
Other questions? No? Great. Okay. Thanks very much.
Just a small difference. There is no S here, so I don't know where the typo was. There will be only one model here.
There's also a hyphen.
All right, so let's start. So the idea here, we're looking at superhydrophic surfaces, and this looks like this at close-up, but these dimensions here can be quite small, of the order of a few hundred microns or millimeter. And if we coat ships or other surfaces which are within a flow, we want to reduce the drag in the flow by introducing these pockets which can contain air, and therefore changing the solid boundary condition with a stress. With this no stress boundary condition, you have slip, and you reduce the overall drag. The problem that we found recently is that if you have surfactants, these can adsorb at the interface and induce a Marangoni force which oppose this effect and reduce the effect. So you lose completely, or potentially completely, the drag reduction effect of the superhydrophic surface. So this is the model that we're going to consider, a 2D model where we have a periodic array of air-water interface. So here, note they are at the top, but that's basically where your air bubble should stand. When there is no flow, the surfactants sit nicely at the interface. That's what they do. They like it. But as soon as you introduce a flow, as we showed in this paper in 2017, then they start piling up at the stagnation points and induce this opposing surfactant Marangoni stress. And potentially at low concentration, you can get no slip boundary condition at the air-water interface, losing completely the advantage that the superhydrophic surface should give you. So let's see how we can model this. So we're going to consider a 2D system. And because this is periodic, we're going to have just one unit of this system with the following geometry. We have in the bulk the Navier-Stokes incompressible fluid equation and surfactant advection diffusion in the bulk. Then at the air-water interface, we have also the advection diffusion equation for the surfactants, where I have gamma, now the concentration of the interface, as people have introduced in the previous talks. There is also the Marangoni stress, which appears here, and the interfacial flux. That's the continuity equation, basically for the flux between the interface and the bulk. You can have a bit of chemistry, so that's the kinetics. These source term and the Marangoni stress depend on some model for the kinetics, which we're going to choose as modified from kinetics.
which I introduce here. So that's this one. So you end up with quite a lot of equations. This can be nonlinear system. It's highly coupled, and you also have a lot of non-dimensional parameters. So these are the 7 non-dimensional parameters for the flow and the kinetics. So you have Reynolds number, Pecla numbers, the Marangoni number here, which can be quite high. And there's K also here, which is this reduced concentration for the bulk. And also in 2D, you have 2 geometrical non-dimensional numbers, the aspect ratio, here G, and the gas fraction. So let's see how we can make some progress with that. First, let's have a look at computing the velocity field, or having a way to predict it. We're going to make a few assumptions. First, we're going to assume that we'll have laminar or Stokes flow. That's going to simplify the Navier-Stokes equation. We're also making an assumption which is going to be valid in some regimes. So we're going to say the gradient of the concentration is uniform, so you have a uniform Marangoni stress at the interface. We're going to see later how this can break down in some regimes. And you can get a solution thanks to very nice work of Logan Stone in 2003 in JFM. They give you this term, but they predicted this term for the surfactant-free Stokes problem. And when we looked at this, we realized that something very nice happens, that even when you have these surfactants Marangoni-induced stress, this decouples from the geometry. So that's really helpful. So this guy is quite complicated, but you can get it analytically, and you have this expansion that gives you arbitrary precision. So the velocity looks like this. If you have so normalized velocity at the center line on the air-water interface, at very small g, as you expect, you go down to 0, so you reduce the air-water interface, and you have the linear behavior that you can capture with some simple asymptotics, and then you experience the viscous effect of filling the opposite wall. So that's the plateau here. This is for low gas fraction. When you increase the gas fraction, then you have these interesting behaviors reaching the maximum value of 1. We haven't quite figured out whether this is exponential behavior. This is still ongoing work, so we're going to look a bit more at this. But this reaches the value of 1, which is the maximum value you can expect in this type of flow. Now we need to have a look also at the surfactants side of the equation. As we say, we have decoupled it. So let's see how we can also make some progress to predict this gamma MA. So we make the assumption first that we have small surfactant concentration. Indeed, you don't want to introduce them. You hope that there are not too many. And so we do some linearization of the transport equation, and we end up with this fairly complicated, but this is almost fully predictive model. You recognize again the function coming from the geometry of solving the Stokes flow problem with the no surfactant in here. And there's also, this is where you need a bit of fitting parameters for this diffusive boundary layer of the surfactants near the interface. So you can get this, and you also note that you have reduced your 7 non-dimensional parameters by 6. You can capture in this concentration non-dimensional parameter and the Marangoni number, they combine together. So we've done a lot of COMSOL numerical simulations, varying all the parameters, trying to see when the model is valid and when it's not. You can also introduce 2 extra parameters, which are based on the work of Palapati for air bubble rising in water. That's the adsorption flux divided by the surface convection, and the diffusive flux divided by the surface convection. We vary across a very wide range of parameters, as you can see. And what are the results? So that's the effective slip length that you can get. So taking the definition of Logan Stone here, so effectively when you reach 1, that's your goal. You have increased the flux as much as you can. And going down to 0, that means that you're really at no slip boundary conditions. So that's bad. So let's see how the model compares. We have a very nice collapse on the line 1, but a few points here which are not quite well predicted, but these, we realize that they're really breaking the model. So that's when the concentration is very high, so above 1. We had the model assumption which was for low concentration. Then for high Reynolds number, so here up to 1,000, it also breaks down. And also when the linear assumption is invalid, then you have also these points which do not quite match, are also not working so well. But that's basically when these D and K number and the surface specular number are of this form. That's correspond to air bubble to the stagnant cap regime that some of you may know. So it's very highly nonlinear regime. And if I plot now the error that we make between the theory and the data, this numerical simulation data, we find that there's an error of sort of the order of 10%, a bit less. At high Marangoni stress, there's a bit more error, but what is important is to compare with the model that you would get neglecting the surfactant effect. So here, that's the blue crosses, and you find that you introduce enormous error if you neglect the effect of the surfactant. So that can be quite bad. You might predict that your ship is going to have a nice drag reduction effect. Maybe not at all. So to conclude, we have here made a model under a few assumptions to try to capture the effect of surfactants on superheavic surfaces and to see when they impact the drag reduction effect. We made these assumptions, which are reasonable in most regimes. And we found that this was also both valid for internal and external, simple external linear shear flows. And we reduced dramatically the problem to a very simple boundary condition that people could use in a DNS, for instance, without having to solve the full surfactant coupled problem of 6 nonlinear equations. And with this, I would like to thank all my collaborators and our sponsors. Thank you very much. This one or the previous one? This one, yeah.
How come some of the circled points are near non-circled ones?
These ones, you mean?
Yeah.
You notice that.
What's the difference between them?
So here, that's effectively when the surfactant gradient is at the interface is not really uniform. There's a stagnant cap regime, so you have a high concentration, very high concentration at the downstream point. So clearly, the linear assumption that I made is invalid. Why it sort of breaks down here, I mean, you are at extremely small.
Why are they near each other?
Near each other, here. Yeah, my point is, this is extremely small values. So here, maybe the model is, the COMSOL simulation might also not be perfect at these very, very small values. So it might be a problem of resolution. Yeah.
If you consider potential application in the real surfactant concentrations you may find as spec 1 concentration C, where would you be, in which parameter range would you be?
So you would get pretty much no slip. That's what we looked at for, I mean, surfactants have lots of different properties, but for typical SDS, the sodium dodecyl sulfate, which is fairly mild surfactant, we found that at concentration reasonably close to environmental concentrations, you have pretty much no slip boundary condition, or a bit of slip, but you've lost a lot of the drag reduction effect. So this is really important to consider. This happens in the environmental conditions.
Good. I think it's time for a coffee break. Let's thank Julian.
Thank you.